Imagine a clock ticking a little differently for you than for someone else, even if you are both perfectly healthy and your clocks are identical. Sounds like science fiction, right? Yet, this is exactly what happens every second in our modern world, affecting technology you use every single day. Global Positioning System, or GPS, satellites are perfect real-world laboratories for observing time dilation. They experience the subtle but measurable stretching and shrinking of time predicted by Albert Einstein's theories of relativity. The observation of time dilation in GPS satellites comes from two main relativistic effects. First, special relativity tells us that a clock moving at high speed will tick slower relative to a stationary clock. GPS satellites orbit Earth at speeds of about 14,000 kilometers per hour, or roughly 8,700 miles per hour. This speed causes their onboard atomic clocks to run slightly slower, by about 7 microseconds per day, compared to clocks on Earth. Second, general relativity states that gravity affects time. Clocks tick faster in weaker gravitational fields and slower in stronger ones. Since GPS satellites orbit at an altitude of about 20,000 to 100 kilometers, or 12,550 miles, they are in a weaker gravitational field than we are on Earth's surface. This weaker gravity causes their clocks to tick faster, by about 45 microseconds per day. When you combine these two effects, the general relativistic effect of faster ticking due to weaker gravity is much stronger than the special relativistic effect of slower ticking due to speed. The net result is that GPS satellite clocks run faster by about 38 microseconds per day compared to clocks on the ground. These tiny differences in time, though seemingly small, are incredibly significant. To ensure your GPS device can pinpoint your location accurately, these relativistic effects must be meticulously accounted for. Engineers design the satellite clocks to be initially set slightly slower or build in direct compensation algorithms. This pre-adjustment ensures that from our perspective on Earth, the satellite clocks appear to be perfectly synchronized with ground-based reference clocks, allowing for precise position calculations. The GPS system's ability to correct for these relativistic time shifts is a remarkable testament to the predictive power of Einstein's theories. Without these precise adjustments, the accumulated error would be so large that GPS navigation would become inaccurate by several kilometers each day. So, every time you use GPS, you are directly benefiting from the application of advanced physics that confirms the dynamic nature of time itself.